Hey guys, so today we're going to be talking about the Michaelis-Menten equation. So what is our Michaelis-Menten equation? Well, it looks like this. Alright, so this is our Michaelis-Menten equation here. Alright, so that's a lot of weird letters, so let's go ahead, let's define some of these. Let's derive this equation from things that we do know, okay? So let's start really simple, alright? We're going to start with an enzyme and a substrate, and those form an enzyme-substrate complex, right? And then those go on to form, we get our enzyme back out, and we get a product. So if we're going in the forward direction here, we call that K1. So that's going to be the rate at which we can form the complex. Well, reversely, the rate at which our complex dissociates is going to be the reciprocal. So it's going to be K-1. And then the rate at which our concentration goes from ES to EP, that's going to be K2, okay? Alright, now, so very simple, right? Well, let's go ahead, let's see what we can do to use these concepts to figure out some stuff in our main equation. Well, so we know that we have some v's in the Michaelis-Menten equation, so that means we're probably talking about velocities, right? So let's look at some instantaneous rates of change. So we're going to look at the instantaneous rate of change for the enzyme-substrate complex over time. So that's perfect because we know that it's going to be equal to 0. So we can use this to determine some of our variables. So we've got our rate of reaction, and anytime we see something in parentheses, we know, or brackets, we know that we're talking about concentrations, right? So anytime I have letters in brackets, we're talking about concentrations. So this is the equation for the instantaneous rate of change for this specific mechanism, okay? So, well, we see here that we've got an E. Well, a lot of the times that E is kind of difficult to define. So we can use this equation, E sub T, total enzyme concentration, is equal to the concentration of free enzymes with those in the enzyme substrate concentration. So we can then further derive our E to be E sub T minus the enzyme substrate complex concentration. Okay, now let's go ahead, let's plug this guy in. So E D T, that's going to equal 0, right? So let's plug in our E. So K1 times E sub T, we'll put a parentheses, sub T minus E sub S, alright? And then that was multiplied by the substrate concentration, then we'll fill in the rest. E sub S, 2 E sub S. So we'll get a better look at this, okay? So we plugged in, we saw for E, and then we went and we plugged it in. Well, what can we do now to further simplify this equation? Well, let's go ahead, let's distribute this K1, we'll multiply it by S. Okay. Oh, okay. Sorry, something on my computer fell, but we're good. Okay, and then let's plug this in. S, T, T. That's going to be equal to K1 times E T times S minus K1 times E S times the concentration of S minus S. Okay, so now we've got this all filled out. Well, let's look. We know that this is equal to 0. So let's go ahead, let's define something. Let's go ahead and work this out. So we know that when we have 0, we can add something to the other side and then multiply and divide out. So I see that we've got a lot of ES concentration. So let's go ahead and put those on the other side, and we can solve for the concentration of ES for enzyme substrate complex. So ES times, we've gone here, K1 times S plus K negative 1 plus K2. Alright, and we're going to set this equal to this because it did not have a common variable. Alright, now to solve for our E sub S, we're going to then divide that side. And E sub S is now equal to K1 times total enzyme concentration times substrate concentration divided by our rates of change 1 plus K2. Okay, so now we've broken it down and we solved for ES. Awesome. So let's see, what else can we cancel though? It still looks kind of big, right? Well, let's go ahead, and I see some K1s here and here. So let's go ahead and cancel those out. Divided by K1. Okay. So this one's gonna cancel, this one's gonna cancel, and then under here we're gonna have to divide all that by K1. Okay, so let's go ahead, let's get a fresh sheet. Okay, now what do we have for our enzyme substrate complex? It's going to be equal to the enzyme total times substrate divided by S plus K1 negative 1 plus K2 over K1. Alright, so now this is what we're working with. Now let's use that and let's look at some different instantaneous rates of change. So we've solved for ES, awesome. Now let's look at the instantaneous rate of change for our product, okay? So we know that the rate of reaction for our product was equal to K2 times ES, right? So let's pull this back up. So we'll look back at this guy. So we know that the formation of our product was dependent on K2 and the concentration of the enzyme substrate complex. So that's great because we've already solved for the enzyme substrate complex. So let's plug it in. Okay, so we've got E of t divided by s plus k2 divided by 2. Okay, so now we've got that. Awesome. But let's further define some of these so we can fill in some of our variables. But we'll go ahead and we'll define some terms first. So we know that v is velocity, so we can go ahead and change this out for our velocity, okay? So let's go ahead. V is going to be equal to k cat, which is essentially just k2, okay? So divided by km. So now we've got velocity is equal to k cat. So that k cat, like I said, is just equal to k2. And it's just how many molecules an enzyme can work with per second. So when those enzymes were working with the substrate, and they were forming product, that was our k2, right? So we just swapped that out for k cat. All right, and then we've also got this whole numerator. So this whole section right here. All right. So let's consider how else could we further condense this equation. Well, so we've got our total number of enzymes working with all of your substrates. So right there, right? So we've got the total number of enzymes right here working with all of the substrate. So these two, or sorry, that's going to be our Vmax. So our max rate is achieved when all the molecules are working together. So we're going to come here. We're going to say velocity is equal to Vmax times the substrate concentration. So when all of our enzymes are working together to form product, we get our Vmax. So we've also got to know how much substrate we have. And then we just plug in the denominator. Okay. So, but now we still got one thing that we're not quite sure of. So what is Km though? We understand everything else, but we don't quite know what Km is. So let's define Km. Km is equal to the Michaelis constant. So it's very important. Okay. So we recall that Km from our previous equation was equal to k negative 1 plus k2 over 2, right? So that's what our Km is equal to. Well, what if the concentration of the substrate was equal to Km? So if it were, then Vmax substrate concentration over 2S, right? Because if it were, it would be S times plus S, so it would be 2S. All right, then our S's can cancel out, and this is equal to 1/2 Vmax. So our Km is equal to the concentration of substrate at which the reaction rate is half of the maximum velocity. So now we've defined all of our variables. So let's go back to our original equation. All right, so right here, this is our original equation, our Michaelis